Hi everyone, my name is Tang Lian. I'm here to present our paper in CVPR 2026, a closed-form solution for debiasing visual language models with utility guarantees across modalities and tasks. As we all know that bias present in web-scale data is encoded in VRM embedding space and propagates into many downstream tasks. The fairness research for VRMs can be roughly defined in two directions. The first one is bias auditing and evaluation, where the goal is to identify and characterize social biases in VRMs and their outputs. The second one is bias mitigation, where the goal is to reduce social bias while preserving visual language utilities and alignment. Our methods falls into the second direction. Here are some technical challenges in debiasing VRMs. The first one is multimodal bias. So cross-modal alignment might spread bias between image and text modalities, making single modality debias insufficient. The second one is training cost. So retraining VRMs is impractical. Adding debiasing module also increases model complexity and inference overhead. The third is attribute annotations. Debiasing often depends on sensitive demographic annotations, which are costly and raise ethical concerns. The fourth is diverse downstream tasks. VRMs span many tasks with different fairness and utility metrics, making unified debiasing difficult. The fifth is utility preservation. Debiasing often improves fairness at the cost of task performance, reflecting a utility fairness trade-off. Additionally, we observe that most debiasing studies focus on single attribute group fairness, while real-world individuals often belong to multiple sensitive groups simultaneously. Here is a table comparing our methods to the previous debiasing methods in VRMs. The key takeaway here is that existing debiasing methods address only parts of the challenge landscape that we mentioned before. In contrast, our method is training-free, data-free, and it can debias both modalities and provides bounded utility loss. Additionally, it supports multiple downstream tasks and explicitly addresses the notion of intersectional fairness. Here is how we define utility and fairness objectives in VRM feature space. So for self-utility, we mean that after debiasing, the embedding should still represent the original semantic content of the prompt or image. For cross-utility, it means that the image-text similarity after debiasing should stay close to the original similarity. And for fairness, prior works debiased through hard orthogonal projection onto the subspace S spanned by group prototypes. The problem is that the subspace S contains both attribute information and useful semantic content, so such hard projection might hurt utility. Our method instead enforces orthogonality only to the attribute subspace A, thereby reducing bias while preserving semantic content. Our proposed method has two components. Component 1 is called LLM-guided group prototype construction. So for the input prompt, we input this prompt into an LLM, and an LLM output two things. The first is group contingent anchor prompt, and the second is the variance of the anchor prompt. So by taking the theoretical mean of the anchor prompt and its variance, we construct the group prototype. And from the group prototype, we can further construct the attribute subspace where the debiased embedding should be orthogonal to. For the component 2, we try to search the debiased embedding U in the unit hypersphere that the embeddings live in visual language models. First, we have this orthogonal decomposition. So for any embedding in the Eclipse cross-model space, we can decompose with respect to the attribute subspace A to the components that is parallel to it and orthogonal to it. And then we can define our objectives. So fairness, we try to minimize the attribute leakage of the debiased embeddings and preserve the self-utility by minimizing the self-utility loss. And we formulate this optimization problem using a weighted sum, and this can be further reduced to a 2D spans and a scalarized problem. And we use Chebyshev scalarization to solve this scalarized problem and use a closed-form solution. Additionally, these closed-form solutions offer very nice theoretical guarantees that self-utility and the cross-utility are both upper bounded. We evaluate our methods across various downstream tasks, such as zero-shot image classification, text-to-image retrieval, and text-to-image generation across various fairness and utility metrics. Here is our results on zero-shot image classification and text-to-image retrieval. As we can see in the tables, our methods deliver competitive fairness performance with the minimal loss of the task performance. Here is the experimental results for the text-to-image generation. For the qualitative examples, the female-looking samples are marked with numbered circles. On the left, there's a neutral prompt, so a more balanced male and female ratio indicate lower bias. On the right, there's a male explicit prompt, so fewer female-looking samples means fewer misgenerations. Our method is also competitive in the quantitative results in text-image generation by having lower SP values and higher flip score. Furthermore, in Table C, the emulation and sensitivity analysis evaluates key components across our methods and the sensitivity with respect to different LLMs. Here is the summary of the presentation. Thanks for watching.